had a smaller hill before I finally reached a product. Thinking through, just by looking at the rate law comes from the slowest step, the one with the largest activation energy. This would give me what's known as K1. And in that faster step, a smaller amount of activation energy would give us what's known as K2, a two-step collision in order to get the reactants to turn to product. Thinking about what we started with, the reactants, we had NO2, another molecule of NO2, and a molecule of F2. We decided the first collision based upon the rate law would be a collision of the molecule NO2 with the molecule of F2. And at the top of that barrier, we formed what was an intermediate. The intermediate was that single molecule of fluorine. We already produced one of our products, NO2F, but at the top of that energy barrier was that atom of fluorine. Notice immediately in the next collision, it hit with the second molecule of NO2F. Immediately made, but immediately used in the next step, we call this fluorine atom an intermediate. Something that's made and then used up in the next step doesn't appear in the overall equation because they cancel. The right side would simplify with the left. F is called an intermediate. It is formed, then consumed in the reaction. Our intermediate that was produced was a fluorine atom as a result of our first collision. And that first collision produced a molecule of our product, but left us with a fluorine atom that then went on to hit with the second molecule of NO2. Each of these two steps is called an elementary step. The rate of the reaction can be written from its molecularity. In other words, how many molecules are actually colliding determines its molecularity. Molecularity, checking its spelling. So the molecularity is a term used to describe the number of pieces that must combine together. If I have something known as a unimolecular step, unimolecular, uni meaning one, what it's involving then is a single molecule just rearranging itself. Not necessarily a collision because it's just a single molecule, but if I rearrange bonds, I could have a unimolecular description. In a bimolecular reaction, it requires two molecules to collide. The rate is second order overall. That would have been the description up above with our first example. First order with respect to NO2, first order with respect to F2, second order overall. A second order rate shows two things colliding together. In a termolecular equation, would require three molecules and the rate is third order. However, be very cautious if you're predicting a reaction mechanism in which three molecules must collide with just enough energy and the correct orientation. It's just that the chances are crazy high. It says termolecular steps are almost never heard of because the chances of three molecules coming into contact at the same time are minuscule. When we're proposing rate mechanisms, stick to unimolecular and bimolecular. Unimolecular is a single molecule rearranging itself. Bimolecular is when a molecule of one thing, second molecule of a new thing collide together, giving us a bimolecular. That's very readily available. But if I want to predict a termolecular, three things colliding, I think it's not going to happen. It's just unheard of that chances of three things being successful in colliding is minuscule. Let's turn the page over and take a look at elementary reactions. It says they're significant and in a very important way. If we know that a reaction is elementary, then we know it's a rate law. each elementary reaction comes directly from a collision, and therefore each elementary reaction has its own rate law. When we look at an overall equation, one that's not based on little elementary steps but many combined together, then we don't know its rate law based on looking. So suppose if I have a product called A, if rate is equal to K times the concentration of A to the first order, we know it's unimolecular. If A collides with the second molecule of A, we would know it's second order. It would be bimolecular, two atoms of A colliding together. Often written instead of A plus A, you could write that as 2 units of A, still a second order. What if we have two different molecules colliding? A collides with B, first order with respect to A, first order with respect to B, but second order overall, it would be considered bimolecular. Then I get into the world that I would not use. I would not predict pathways that involve termolecular collisions. If 2 units of A collide with B, we get third order overall. I would not predict that to be an elementary reaction. Same is true for the rest of those examples. If I'm predicting 3 molecules simultaneously collide with just the right orientation, I would not use that as an elementary, but instead predict these to be overall equations in which the pathway has been added together. So let's take a practice. It's been proposed that the conversion of ozone gas into oxygen gas proceeds by a 2-step mechanism. In the first step, one molecule of ozone breaks down into an oxygen molecule and an oxygen atom. The second molecule of ozone, O3, then collides with that oxygen atom to produce 2 units of O2. Let's take a look at the molecularity for each of the elementary reactions, elementary reaction 1 and elementary reaction 2. In the first elementary reaction, we had a single molecule of ozone just reorganizing itself to create an oxygen molecule and an oxygen atom. It is a unimolecular elementary reaction, a single molecule rearranging. In the second elementary reaction, we had that ozone molecule hitting the oxygen atom that was formed above. That collision between 2 atoms would give us a bimolecular elementary equation. If we're thinking about the sum of those equations together, we would get the overall reaction. Adding together elementary reaction 1 and elementary reaction